in this module we study the transportation problem. The transportation problem is a very important topic in linear programming and in operations research. Let me explain the transportation problem. A network is shown here which has some nodes or vertices which are connected by arcs. Now, the transportation problem talks about transporting a single commodity or a single item from a set of supply points or points where the item is available to destination points or demand points where the item is required. So, this network shows a transportation problem where the item is available in 3 supply points which are shown here. It is available in 3 supply points. This is the supply point 1, this is the supply point 2, this is the supply point 3. So, it is available in 3 places. The quantity available are given by these numbers 40, 25 and 35 units of this item are available in these 3 supply points. Now, the other 3 points are the requirement points or the demand points. Now, these 3 are the demand points and the requirement is 30, another 30 and 40 in these 3 places. Now, the problem is to transport the available items from the places where they are available to the places where they are required. Obviously, there is going to be a cost of transportation. Now, this cost of transportation is given as a unit cost. For example, this 8 is the cost of transporting 1 unit from this supply point 1 to the demand point 1. We can call this as supply point 1, this is demand point 1. So, this 8 is the cost of transporting a unit from supply point 1 to demand point 1. Similarly, this 5 can be taken as the cost of transporting 1 unit from this supply point to this demand point. So, since there are 3 supply points and 3 demand points, there are 9 ways of transporting them and you are able to see 9 costs that are written here. Unless otherwise stated, the transportation problem assumes that it is possible to transport from every supply point to every demand point or destination point directly. You will also observe that in a transportation problem, while you can supply directly from supply point 1 to demand point 1, you do not transport them from one supply point to another or from one demand point to another. The transportation problem does not permit us to model such a situation. So, transportation is permitted from supply points to demand points directly. So, there are a set of supply points. In this case, in this example there are 3 supply points. There are a set of demand points. In this example there are 3 demand points. We should also note that it is not necessary that the number of supply points should be equal to the number of demand points. We could have another transportation problem where there could be 5 supply points and 8 demand points, unequal number of supply points and demand points. We could even have a situation where there are 8 supply points and 6 demand points and so on. Now, the problem is how do I transport this 40, 25, 35 to meet the demand of 30, 30 and 40 such that the total cost of transportation is minimized. This is called the transportation problem. Now, let us understand the transportation problem further and let us try to formulate this as an OR problem. So, let Xij be the quantity transported from I to j. Now, in this notation, I represents the set of supply points and j represents the set of demand points or destination points. It is customary to represent the supply points on the left hand side and the demand points on the right hand side, and an arrow indicates that there is transportation from a supply point to a demand point. So, let Xij be the quantity transported from supply point I to demand point j. Now, obviously, we want to minimize the total cost of transportation. So, the objective function will be to minimize summation over I, summation over j, Cij, Xij. Now, since there are 3 supply points, I is equal to 1 to 3, since there are 3 demand points or destination points, j is equal to 1 to 3. So, there are 9 Xij variables. There are also 9 Cij or unit cost coefficients. The unit cost coefficients would be 8, 9, 7, 4, 3, 5 and so on. So, if Xij is transported from this 1 to 1, if Xij is transported from this one supply point to this, each unit transportation is going to cost us 8, therefore, the total cost will be 8 into X11. Since this transportation can happen in 9 ways, so the objective function will be expanded to minimizing 8x11 plus 9x12 plus 7x13 plus 4x21 plus 3x22 plus 5x23 plus 8x31 plus 5x32 plus 6x33. So, there are 9 terms and these two summation signs I equal to 1 to 3, j equal to 1 to 3, Cij, Xij will give us these 9 terms, and that summation is to be minimized. Now, what are the constraints? The constraints to this problem will be sigma Xij summed over j is less than or equal to Ai. Now, I equal to 1 to 3. So, let me explain this constraint. Now, Ai are the supply quantities that are available. So, Ai are the supply quantities that are available. So, Ai are the supply quantities that are available. So, A1 is this 40, A2 is this 25 and A3 is this 35. So, what does this constraint tell us? Summed over j, Xij is less than or equal to Ai. Suppose I take the first supply point which has 40. Now, from this supply point I am transporting to this, something to this, something to this. I may transport, I may not transport. But whatever that comes, this 40, whatever is available in this 40 only can be transported. So, if X11 is going here from this point from 1 to 1, X12 is going here and X13 is going here, then X11 plus X12 plus X13 is the total quantity that is going out of the supply point 1, and that should be less than or equal to the available quantity, which is 40. So, there are 3 constraints here, one for each supply point. For the first point, the constraint will be X11 plus X12 plus X13 is less than or equal to 40. For the second supply point, which has A2 equal to 25, the constraint will be X21 plus X22 plus X23 is less than or equal to 25. For the third point, it will be X31 plus X32 plus X33 is less than or equal to 35. So, there are 3 constraints here which are represented in the form of a single expression, and there are 3 constraints for each, one each for each of the supply points. Now, continuing, we have the second set of constraints which says sigma xij summed over I is greater than or equal to Bj. Now Bj is represents the demand in these demand points. So Bj represents the demand So Bj represents the demand. There are 3 demand points which are here. The values are 30, 30 and 40. Now if we take the first demand point with 30, now the demand of 30 has to be met by sending things from these 40, 25 and 35. So x11 is sent from this 40, x21 is sent from the second supply point, x31 is sent from the third supply point. So for this x11 plus x21 plus x31, here is x11, this would be your x21 and this is x31 in this arc. So x11 plus x21 plus x31 comes to the first demand point and that has to meet the demand, therefore it has to be greater than or equal to B1 which is equal to 30. So again there are 3 constraints, one for each demand point. The first demand point constraint will be x11 plus x21 plus x31 greater than or equal to 30. So summation I is equal to 1 to 3. The second one will be x12 plus x22 plus x32 is greater than or equal to this 30, which is the demand in the second demand point. And the third constraint will be x13 plus x23 plus x33 is greater than or equal to 40. So there are three constraints, 3 demand constraints. And then we have the non-negativity restriction xij greater than or equal to 0. At this point we may ask a question, should we transport integer quantities or can the quantities be continuous variable? And we are now going to assume that the xij's, which are the quantities transported, are continuous variables to begin with. So this is the formulation of the transportation problem. So if I have m supply points, customary to use this, if there are m supply points, if there are n demand or destination points, then the number of variables xij is equal to mn. So number of variables is m into n. In our example we have taken m is equal to n, both are equal to 3. So we had 9 variables, otherwise it is mn. And then there are m supply points, so there will be m constraints here, one for each supply point. There are n demand points, there will be n constraints here. So it will have m into n, mn variables and m plus n constraints and a non-negativity restriction. Now the next important thing that we need to look at is a transportation problem is balanced when total supply equals total demand. So what do we convey through this? Now there is a demand of 30, 30 and 40, 100 units there is a demand. Now we are going to assume that we have enough quantities in the supply points so as to meet this demand of 100. So obviously this problem when we solve, if we should meet the demands of all the destination points and if we should meet all these, the supplies or total availability should be greater than or equal to the total requirement. Only then we will be able to send sufficient quantities to meet all the requirements. Let me come back to this formulation again, and the formulation talks about minimizing sigma Cij Xij, double sigma Cij Xij, subject to summed over j Xij is less than equal to Ai, summed over I Xij is greater than or equal to Bj, Xij greater than or equal to 0. Now this formulation has a linear objective function. in terms of the variables xij, constraints are linear inequalities and there is a non-negativity restriction. Therefore, this problem is a linear programming problem. So, the transportation problem is a linear programming problem. That is the first thing that we observe, is that the transportation problem is a linear programming problem. Now, let us come back. Now, for this transportation problem to have a solution, which means for us to meet all the demands and satisfy all the demand constraints, the total supply should be greater than or equal to the total demand. So, for this problem to have a feasible solution in the first place, then sigma ai should be greater than or equal to sigma bj. Total supply is greater than or equal to total demand. A further look into the problem will also tell us that if the total supply is greater than the total demand, because the demand in this problem is total demand is 100 or in any quantity sigma bj, we will not transport more than what is required for every demand point, because transporting an additional quantity over and above the demand is only going to increase the transportation costs. This is under the assumption that all the unit transportation costs are non-negative or positive. Therefore, even if the total supply is greater than or equal to the total demand, we will not supply more than the demand for an individual demand point, and therefore, the problem becomes nice when we have sigma ai is equal to sigma bj, which means when the total supply is equal to the total demand, we will have a feasible solution, we will be able to meet the demand, and the problem will not be different if the individual supplies were when the total supply is actually greater than the total demand. So, even if the total supply is greater than equal to total demand, it is enough to have a problem where the total supply is equal to the total demand to solve and get a solution to this. So, when the total supply equals total demand, which is shown here, this problem is called a balanced transportation problem. So, sigma ai is the total supply, sigma bj is the total demand. So, this problem is called a balanced transportation problem. Now, first let us check whether our problem is balanced. The total supply is 40 plus 25, 65 plus 35, 100, 30 plus 30, 60 plus 40, 100. So, sigma ai is equal to sigma bj. So, our problem, the problem that we are looking at as a numerical example, is a balanced transportation problem. But we have also seen that this transportation problem is a linear programming problem. So, if the transportation problem is a linear programming problem involving m into n variables and m plus n constraints, then we could solve the linear programming problem directly. But before that, let us also understand what is the implication when total supply is equal to the total demand. When total supply is equal to the total demand, finally we will have a situation where we use up all the supplies that are available and we also meet the demands exactly, because total supply is equal to the total demand. So, when the total supply is equal to the total demand, the balanced transportation problem can be written by replacing these inequalities, with the equation that is written here. So, replacing it with the equation. So, the constraints become sigma xij is equal to ai and sigma xij summed over I is equal to bj. So, the linear programming problem for a balanced transportation problem will have equations instead of inequalities. It is a linear programming problem and we could think of solving this problem as a linear programming problem using the simplex algorithm and so on. But if we look at this example that we are talking, we will have 9 variables and 6 constraints, and it would become difficult for us to solve it using the simplex table. Of course, if we are using solvers and other ways to solve it, it is a little easier to do that. But then over a period of time, people who have studied the transportation problem also understood that there are good, efficient and faster ways to solve the transportation problem than solving it as a linear programming problem. Now, the transportation problem therefore has special methods and techniques which are used to solve the transportation problem in a faster, quicker manner compared to solving it using the simplex table, even though it can be solved using the simplex table. Now, these faster and quicker methods also use ideas from linear programming and duality that we have seen earlier in this course. In the next class, we will look at what are these special methods which can solve the transportation problem nicely and solve it faster than perhaps solving it using the simplex table.